Hi class, welcome back to our Materials Informatics series. Today, we're going to pick up where we left off. Last time we were talking about the composition-based feature vector, and it's fantastic. It's a really great way to add information to our machine learning model from Chemical Insight. But it doesn't tell the whole story, and that's why today we have to talk about the structure-based feature vector as well. Now, why? Let's start with this slide. What you see here is, I think, a really great example of why we need to care about structure as well as composition. Carbon. Think of carbon. You are familiar that carbon has many different allotropes, right? Allotropes are different formations or structures for something that is the same element, or polymorphs we call them if it's a multiple element compound. Carbon has a ton of different allotropes. You've got diamond on the top left here. You've got graphite, but then you've got all these other ones. You've got Lonsdaleite, Buckminster Fullerene. This comes from the wiki page on it. There's tons of them. Right? Now, not every compound is as complicated as carbon, but in general, structure is needed if you're going to tell the whole story because many things can have the similar chemistry but very different structure. And think of the differences in properties between graphite and carbon, for example. Wildly different properties there because structure matters. So I think it's going to be important for us when we're thinking about ways to represent and featurize materials to also know how to do it with structure. So this video will discover, we're going to talk about, first off, how can we do it? Right? And then what are the things that we should be doing? So let's start with what are the features that we should be thinking about? Well, previously we'd said that there's lots of things that go into material science and that structure as a general term can mean a lot of things. From the really small scale, from the electronic scale, we could be talking about it in that way, or rather in the atomic scale, sort of crystal structure scale, the microstructure, or even macro scale. So if it can exist across all these length scales, what are the sort of things that we can quantify? Let's start with the smallest scale, the sort of atomic level. Well, one thing that you probably are aware of from your general chemistry or P-chemistry class is that the atomic structure, we have a way of describing the structure, right? There's all these different shapes of these orbitals, but they can be described with the 4 quantum numbers, right? You have your principal quantum number, you have your orbital angular momentum quantum number, L, you've got your magnetic quantum number, M sub L, and your electron spin quantum number, M sub S, right? With these 4, we can describe all these different structures, and there's rules, right? We know that N, the principal number, quantum number, can be integer values, but L can be integer values up to N minus 1, right? And then M sub L can be everywhere from negative L to positive L in integer values, right? There's these specific rules that they can be, but if you have those, all of a sudden we have a way of describing or featurizing the structure of the atoms, which is really great. The only problem for us is that this isn't a perfect tool for what we need because the fact is we're not trying to predict the properties of single atoms very often. We're much more interested in predicting the properties of full-on compounds, right? And things change when you form compounds. Bonds change. They hybridize, right? We get the effects of geometry, right? Where different orbitals are now close to one another and they impinge on one another, push things around, they become bulbous, they change their shape a little bit. How do we quantify that? Is a much harder question. Now, one way that people thought to do this is by using diffraction. If you've taken a diffraction course in material science, you know that X-rays come in, they interact with matter because it's on the similar length scale, and then it reflects off. Well, we can take that information as it's reflected off, and we can actually determine what caused it to scatter, and we can actually create sort of curvatures or electron density maps, right? Regions of how dense the electrons must have been in a structure to get the diffraction data that we observed. So for example, this is from a paper that I did with some colleagues 5 years ago with the brilliant Anton Oleanik, friend of mine. We were looking at this family of materials in the gadolinium cobalt bismuth system, and we were looking at the electron density maps because it looked like there was these 2 cobalt sites and that there might have been another one in between them. And sure enough, in the electron density map, you see regions of high electron density where the 2 cobalt 1 positions are, and there was a smaller region, a less dense region in the cobalt 2, which means it's less occupied. So these are sort of a proxy because we don't have a great way of describing the full complexity. It would be very hard to do so. These are a nice proxy where you can get density maps and treat it, instead of knowing all the number of electrons, you get a density estimation of what the electrons must be spatially through material. So that could be a good feature, right? You could take this and grid it out or put it into a 3-dimensional voxels, and that could be useful information for you. What else? Well, crystal structure. Moving from electronic and sort of atomic level, let's zoom out a little bit to the crystal structure level. When we think of the unique aspects of the crystal structure that might be useful for features, what comes to mind? Well, for one thing, think of bonds, right? Materials, crystal structure are made up of things that are bonded together. So under the category of bonds, we could ask, well, what type of bond is it? Is it primarily ionic, primarily covalent? Is it a metallic? Is it a weak bond or a strong bond? We could ask those questions. We could ask what elements are involved in the bond, right? Is it a bond with another atom of the same type, boron to boron, for example, carbon to carbon? Or is it two different materials, sodium and chloride, right? What's the length of that bond? What's the distribution of the electron density across that bond, right? There's all these things that could be interesting ways to featurize something about the structure. We could also, instead of thinking about it just in terms of the bond, maybe we want to think about it in terms of the local environment, right? So things like the coordination number, right? For example, this atom in the center is coordinated by what? 6 different oxygens around it, whereas this one is coordinated by 4. There's different coordination numbers. And with that comes changes in the angles, right? We know what the angles are in this one. These are all essentially, if it's a perfect octahedra, these are all right angles. They're orthogonal to one another, whereas these ones are not. These are 109.5 if it's perfectly distributed around. And if it's not perfectly distributed, what are those angles, right? Because these things can be distorted. Take, for example, the octahedra. If this it's sort of like 2 pyramids set top and bottom to one another. If you stretch that arrangement out, you can form distortions, like the Jahn-Teller distortion. And if that's the case, well, maybe we can quantify that as well. That would be information we could quantify. Another way to think about the crystal structure is to sort of zoom out even further and instead to think of it in terms of these polyhedra, these connections, right? Are these isolated polyhedra? Are they corner or edge shared? Are they face shared? How do these things come together? You can see on the left, these ones are corner shared. These 2 polyhedra, which are tetrahedra, are connected by 1 atom along the corner. Whereas these are our octahedra from before, and they are connected along an edge, right? They share an edge, a common edge. But, we could have thought of another one where they share a common face, right? So those are different types of polyhedral connectivity, okay? The angles obviously can change, right? If you look at this one, it's not like it's connected in a linear fashion. Dog. They can be connected at angles or at different distances. So those are all things that we could consider, okay? Now, another way to think about structure, crystal structure, and the features that could be present is to ask ourselves, well, maybe the features that really matter are at a slightly more zoomed out level at the atomic or at the unit cell scale, I guess we could say. Take this structure. This is ferrostulp anomaly, a material I studied a bunch when I was in grad school. Funky structure. You can see it. It's clearly a layered structure. Looking at it from the side, you see that there's these 4 different sort of blue SiO, 4 octahedral layers. And then you've got this other layer, which is I think it was an iron oxide layer in the center. But what was interesting is that if you look closer at this is what you start to see, that these top layers, layer number 1 and layer number 2, if we can call them that, they're different, right? Layer number 1 is made up of a bunch of distinct islands of these 6-member rings of SiO4s. Whereas this layer number 2, is made up of larger islands, right? There are 1, 2, 3, 4, 5, 6, 7 of these sort of hexagonal 6-ring units that have clumped together to form an island. And then if you actually can overlay these, and you can see that layer 1 actually bridges, these small islands bridge the larger islands. So anyways, how do you quantify all this, right? Because that clearly could be important for properties. Maybe transport first has to happen along these larger islands, and then it's connected through the smaller islands to the next layer. That's actually what happens here. So these are all features that we need to figure out a way to how to featurize them to represent them in our machine learning model, okay? Another thing to think of is that structures at the crystal structure level are often made up of slabs. It turns out to be a really convenient way to describe structures, and it's true for a lot of these more complex materials. For example, on the going from left to right, we have the Arrhenius phase, which is made up of you see clearly a perovskite block, a distorted one, and then you have these fluorite layers. That's a fluorite layer. Now take the middle one. This is beta alumina, a really important fast sodium ion conductor, and it can be thought of as having these sort of partially unoccupied sodium channels, but separated by spinel blocks. So it's a slab of spinel separating those. Or on the right, you've got the Ruddlesden-Popper crystal structure, which is made up of, again, perovskite layers, and this time they have rock salt layers. So the slab model approach is also an important feature to keep in mind when you are thinking about crystal structure and structure in general. Maybe it's chains or planes of atoms that can define properties. Many materials, that's certainly the case. Maybe in this one you see clearly there's planar squares and planar hexagons, but these are interconnected via puckered layers. How do you describe those features, right? Those are features. They're clearly there. They could dictate properties. How do we represent them? Here's another one where you can see chains of one-dimensional chains of atoms or planes of atoms that can, again, dictate properties especially in an anisotropic way. Something that often gets left out, I think, of this space is that negative space that is unoccupied by atoms, well, that may well be the defining feature for the given property. This is the apatite crystal structure, and when we were looking at conductivity or even thermal conductivity as well as ionic conductivity, the presence or lack thereof of materials in these channels can really govern the properties. So how do we define negative space? And this is true in many other things. I already mentioned in the beta alumina example that these channels that are sort of partially filled with sodium, well, that's important because that allows more sodium ions to travel quickly along those directions, right? Same thing in many other structures. Take this one. This is the scutterudite. In the scutterudite crystal structure, you've got an atom in the center, which is coordinated by a large number. I think it's 12 around it. And so because of that, it technically could be a really large atom that would fit in that large cage, but it's not. And so it rattles. It's too small. And that being too small, can be important. Anyways, so lots of things at the crystal structure level. Then we can ask another question about structure. We could say, well, maybe it's actually the symmetry, right? The symmetry is incredibly important. When any introduction to material science student learns early on that there are 7 different crystal systems, right? There's your cubic, triclinic, monoclinic, orthorhombic, tetragonal, hexagonal, right? All 7 of those. But then if you take a crystal system and then you add to it different centering operations, centering, not at all, that's primitive, base centering, body centering, or face centering, if you combine these different ones together, we quickly find out that there are 14 Bravais lattices, 14 fundamental different lattices that can be formed, right? But then the shape and size of these lattices can be different. They can have different lattice parameters, right? We often think about these in terms of lattice parameters, A, B, and C. Let's look for orthorhombic, yeah. A, B, and C. Those might all be different values, right? So quantifying those could be important. But the angles don't have to be fixed at 90 degrees either. In some of these, you can have odd angles, right? In fact, for some of these, monoclinic, for example, you need to have multiple, you have to have even more information is required to fully define the structure. So you can end up with angles alpha, beta, and gamma, lattice parameters A, B, and C. You have to know the centering. In chemistry, they call these the 32 Schoenflies point groups. Anyways, in inorganic chemistry, there are the 230 different space groups, meaning there are technically 230 unique crystal structure symmetries. So maybe we need to include this information when we featurize our material. Maybe it's just the space group number we can include between 1 and all the way to 230. Or maybe we need to take into account what is it that makes these things different, right? Actually use the structural information of lattice parameter or angles or centering as part of our featurization, okay? So let's talk about that a little bit more. How are we going to encode all of this information? It's clearly important. How do we encode it? Because I can talk to you about it and you can sort of understand, oh yeah, there are slabs and that's probably important. How do I train my model to recognize those things? How do I help it understand that those are important? Well, we have to represent them in some way. One way to do that would be to do something called one-hot encoding. One-hot encoding is basically a great way of encoding something that is categorical in nature, right? All these different things are categories. Like, is it layered? Like, here's our different features on the left. Is it layered? Are there channels? Are there rock salt blocks? Are there octahedra present? Are there tetrahedra, right? On and on and on. Is it corner sharing? Is it edge sharing? We could, all the things that I just finished talking about, we could create a great big long vector with that same dimensions, the same number of features we have. We can make that vector that length. And then we could put yes or no's, right? That's one-hot encoding. You basically say, yes, it's there, or no, it's not there. And if you do that, let's see how this would look for some of our different materials. Here we have a couple of different materials we saw previously. You've got your Ruddlesden popper phase, your Arvilius, your spinel, and your rock salt. And let's just do this simple example. We could ask, is it layered? Does it have a clearly layered structure? In a couple of these, the answer is definitely yes. In the other ones, no, it is not. Are there channels? In one of these, there's clearly a channels. In the others, maybe there's not. Are there rock salt blocks? Yeah, for 2 of those, there would be. So you can see how these 1s and 0s start to now look unique. This string, like this array of 1s and 0s, becomes a unique fingerprint to each material. And therefore, it's a feature vector, right? We've created a feature vector through just one-hot encoding. Maybe that's a good way to go about this, right? This is certainly one approach to quantifying these otherwise difficult to quantify structural feature vectors, okay? But there's other ways. One way we could do it is to, another way to do it would be to think about the whole entire crystal structure as a 3-dimensional object and to break it up into voxels. So just like a pixel is like a little point in a two-dimensional image. A voxel is a sort of point in a three-dimensional object, right? It has some small volume, right? So we would grid this thing out, right? This crystal structure, this is fluorite. We grid it out, and then we say where, if we did a small grid, would each grid at every point, would it be filled with an atom or not filled with an atom? And then you could start to color it differently. You could say 1, there's an atom there. 0, there's not an atom there, right? But then do you put it there if the atom is centered on that voxel or if any part of the atom is present, right? There's different ways to sort of do it. And then the other thing is, like, what if you don't just care about is there an atom present, but what type of atom? How would you encode that sodium is here and chlorine is here if you're just saying atom yes or no? Then, think of images. With an image, you have like red, green, and blue channels. And with that, you can see in color, right? Because you're combining those different channels. Well, we could do the same exact thing here. We could take our three-dimensional voxels, right? But instead of just encoding it with one channel of yes or no, black or white essentially, which only says atom or no atom, we could give it additional channels to represent the different atoms if we wanted to. That could be maybe one way to do this, where you have a channel for hydrogen, a channel for helium, a channel for lithium, and so on, right? That might be one way to do it, okay? And that would allow us to encode for different atomic chemistries, perhaps, okay? Zooming further out from just the crystal structure, where we've been for a minute, let's talk about the microstructure. The microstructure, here I've shown 4 different microstructures just so you can get a feel for like how wildly different microstructures can be in material science. And this is far from everything, right? There are so many more, and so much of material science involves microscopy because we need to see and quantify the structure. But what exactly are we quantifying? When you look at these images, what information is present? Well, when I look at them, here's a couple that come to mind for me, right? You could say maybe there's the presence of special features like dendrites. We see dendritic formation in an alloy. Maybe that's really important for properties. It is actually. The grain boundaries, those are clearly important. Where are they? How many are they, right? The texturing, what's the orientation of the crystal structure of the different phases that are present? What's the phase fraction? If you've got multiple phases, how much of one phase, how much of the other, how much of a third, right? That's important. The presence of dislocations or imperfections, stacking faults, things like that are important. The grain shape itself matters. Oftentimes in the cartoons, when you first learn about material science, everything is sort of very simplistic, sort of spherical-ish grains. But in the real world, as you can see here, you can have all sorts of crazy distributions of grains. Their size, their shape, distribution can all be sort of off. And then there's porosity, right? There's regions where maybe you don't have matter at all. There's porosity. And maybe it matters how that stuff gets connected together. So tons and tons of structural information, which could be featurized to our benefit, because certainly these things matter, right? We know that they matter for properties. We just need a way to represent them effectively for our machine learning models. So how do we identify and featurize them is largely an open question right now. There are some ways. For example, there's a field known as image segmentation, and we will have a video on it later this semester. But essentially it says if I give, this given input, which I collected from an actual micrograph, you could have a human interpret this and try and label it, right? And so there's been lots of really cool studies where a human has gone through and labeled, well, this is one phase, this is an interface between them, this is a certain type of, whatever defect or whatever. But lately, machine learning models using unsupervised learning have been able to identify, right? They've been able to segment, image segmentation, segment out these different regions and quantify them in an automated fashion. So humans are taken out of the loop, right? This allows us to have the high throughput, potentially better accuracy. A lot of really great things are coming out of that. So more on that later. This is a great paper by Liz Holmes' group, I think. Another way to do it is to think about microstructure in terms of if you have multiple phases present, maybe you care about how they're distributed one from another. So this is a field known as two-point statistics, innovated, as far as I know, by David Fullwood, Stephen Yazgoda, and Surya Kaladindi, a bunch of great scientists at BYU, Ohio State, and Georgia Tech, I think. Essentially what it does, it says if you've got two different phases that are present, what you might do is pick a vector in some direction, at some length and at some direction through your material. What's the odds of you landing on the same phase where you started? So how could you do this? You could do it in 2 approaches, and this is from a really great blog I found where they show that there's a sort of frequentist approach on the left and a Bayesian approach on the right. In the frequentist approach, you take that same vector, this red and this orange line, they're the same vector, right? You take those, and at every single point in this plot, you just draw it on there. And if it lands on white, then you called that a red arrow. If it lands on black, then it was a orange arrow. And you just divide the number of red arrows by orange, or or red plus orange, I guess I'd say, right? You're taking a frequentist approach to analyze this. Whereas a Bayesian approach would instead say, all right, if you had like a starting point and an end point, and you moved this randomly across the image, what's the probability now that you would end on a white pixel or a black pixel or both, right? So different ways of calculating this, but it's useful. And we're going to have another video on this, but just quickly, let's say that your microstructure looked like this to start on the left, right? Maybe it was some sort of block copolymer that's segregated, and you can clearly see that there's sort of like a periodicity in how it segregates. There's a length there that it's sort of obeying when it's segregating. How do you quantify that? And is there a dimensionality? Is there a direction that it preferentially does this on? You can quantify that with this 2-point statistics approach. Here's an example in B and C where they're showing you autocorrelation and correlation of the other phase using 2-point statistics. So future video on that, and we'll have a little bit more on it. But it's a great way to take a complex image and to pull out a feature vector of information about where those two phases are in relation to one another. Okay. There's more. There are tons of custom tools out there for structure featurization. We're not going to be able to cover all of them in this class. We're going to talk about a bunch, and I'll try and just keep on adding videos over time about these. But, there's microstructure segmentation analysis. There's a great set of tools here from PyMKS. This is from Surya Kaladini's group at Georgia Tech. Python Materials Knowledge System, I think is what it stands for. You've got molecules, right? Big organic molecules. How do you represent an organic molecule? Well, since the 80s, we've been using what are called string representations of molecules. So smiles strings versus selfies strings. We'll show you a little bit more on that in a future video. But essentially, if you take this big molecule, you can represent it with a series of text strings of letters, and it'll be able to reconstruct what the molecule actually looked like from that text string. And once you got that text string, you could use that as your feature vector, right? There's the Coulomb matrix, which is essentially creating a grid of the Coulombic interactions of all the different elements in your molecule or structure, whatever you're dealing with. You could just take the three-dimensional coordinates of where the atoms are in a material, right? If you know what the three-dimensional coordinates are of a molecule or a crystalline lattice, you could take those coordinates and use them. There are crystal graphs, which will be the subject of our next video. There are fingerprints, which are kind of a cool idea where you start with a point on this lattice and you say within some radius of that point, what's the local environment, right? So it's sort of like a zoomed out version of the coordination number, which we mentioned previously. For molecules, that makes a lot of sense. Fingerprints are a pretty cool way of encoding information. Bag of bonds, electron density, lots and lots of stuff here. So we will do a couple future videos. But in our next video in this series, I do want to talk more about crystal structure graphs, because graphs turn out to be a really valuable way to represent materials knowledge. We're going to talk about it in our next video.